Hello, class. I have a very interesting lecture for you that's really a comparison of different styles of torsion rods. But before I do that, before I get into that very interesting example comparing different torsion rods dependent upon their different polar moments of inertia, I am going to talk just generally about using the two equations that we've already learned. Let's put them up here. So we've got theta equals TL over JG, right? That's one of our equations. And our other equation is that the maximum shear stress in that torsion rod is going to be TR outer, right? Everything always in torsion always fractures at the outside and makes its way in. Always remember that. Does it fracture on the outside in torsion first, or does it fracture on the inside in torsion first? And of course, at the center of a torsion rod, there is no stress. At the very center of a torsion rod, there is no stress. So in torsion, things always fail from the outside in. All right? They fail from the outside in. And that's the same in flexure. All right, let's use these two equations. Now I want to look at a couple different J's. So the polar moment of inertia for a solid cross section is going to be pi r to the fourth divided by 2. All right. Now, and that's the polar moment of inertia, of course, for area, and the polar moment of inertia for a hollow cross section. Now, when we say a hollow cross section, where's the line there that we cross over? Well, that is still going to be pi over 2, but now what it is, it's the outer radius to the fourth minus the inner radius to the fourth. And you'll see that there's a difference here, than the mass moments of inertia that we worked with, because this is a minus, which is what you would expect it to be. And that's for a hollow cylinder. Now, you're probably wondering, what is the difference between solid, hollow, and a thin wall cylinder, right? So in fact, I want to draw. So let's say that I've got a solid cross section here. Right? So I've got a solid cross section, and that would be what J would be for that solid cross section. That's a 4. Hollow cross section. Now, a hollow cross section really takes everything, that's hollow all the way down to about 5%. So anything that you've got, I wouldn't say, let's say 10%. You could use thin walled approximation at 10%. But usually when we're looking at a hollow torsion rod, we're usually looking at about 80% of the core is being cut out. And so what's left of the cross section, I guess I can do this in black. What's left of the cross section is the other, 20% of the radius that we still have. So when I look at a hollow cross section, I'm assuming that the bore that's been cut out, now here you can see it's probably about 60% or 50%, but I look at it as being about 80%. And so what we're going to do in the comparison today is we're going to say that for the hollow cross section, that the outer radius, the inner radius is going to be 80% of the outer radius. So that's something that we're going to be analyzing. So my inner radius, let's just say for the hollow, my inner radius is going to be 80% of my outer radius. Right? That's just something, we just want a relationship between the inner and the outer radius. We're going to need that for when we compare a hollow shaft, which would be like the drive shaft in your car. Have you ever gotten under your car and looked at the drive shaft if you have rear-wheel drive that goes from the engine to the rear-wheel drive on your car? You can see this drive shaft very easily under trucks, you know, that are not semis, but you know, moving trucks and things like that. Underneath, you can actually see the drive shaft spinning. That happens to be a hollow cylinder, and the reason that we make it a hollow cylinder is more for the flexure. If I made it just a solid cylinder, the thing would flex too much and be, you know, breaking itself. So we've made it with a hollow cylinder. Could we make it with a thin-walled cylinder? You know, there would be other problems that we would run into with a thin-walled cylinder. So we want it to work in a flexure mode too. So that's that. Then the thin-walled moment of inertia is 2 times pi r cubed times t. And basically what we're saying with this is that, and thin wall, I want to describe that. So R of thin wall has to be less than or equal to 10% of the wait a second, yeah, of the outer diameter, outer radius of the thin-walled. So we're basically going to have something that's only 10% of that. You know, if I wanted to look at it as a hollow cylinder, I mean, I can actually make it 5%, and that's what I'm going to look at in this thing. So, you know, if it's 0.05 times the outer diameter, outer radius diameter, same thing, because we're not squaring anything here. So it's going to be the same as the outer. So the thickness, in fact, what I should put there, what I should put there is that the thickness, not the inner radius or whatever, the thickness of the wall of a thin-walled cylinder, T. That's the T right there. So T is going to be less than or equal to 5% of the outer radius of the thin wall tube. All right. Or you could say it's 10% of the diameter. 5% of the radius, 10% of the diameter, exactly the same thing, right? So we'll use that. But before I ever do that, before I get into all of these things that we have just talked about, I want to do a very simple problem where we look at a torsion rod. All right, so here's the simple problem. Let's just take that torsion rod that we had before. I'll draw it over here. Right, so we've got the torsion rod. I'm going to give this some dimensions in just a second. And we're torquing on this, right? So we've got some applied torque here, and then I'm going to have a resistive torque here, right? T resistive, because it's not rotating at all. So we know that the two torques have to offset each other. This end is not moving, this end is moving. I do know a couple things about, let's just look at that diagram again. I do know how much this has twisted. All right, so we know a couple things with this example problem. So let's just put our example problem up here. And we know a couple things. We know that it's steel. Right, I've got a steel torsion rod that's a solid cross section. So we know that it's steel. We know it's a solid cross section, so we know that J is going to be equal to pi r outer to the 4th over 2. Right, so we know that. That's what our J is. We're getting all of our stuff together. You know, if it's steel, we know a couple things about it. We know that for steel, my modulus, wait a second, what am I? I'm not even dealing with Young's modulus anymore. I just think modulus and I immediately write Young's modulus. No, our modulus, everything in shear, everything in torsion is in shear. Torsion equals pure shear. Torsion equals pure shear. Everything that's done in torsion is in shear, not in normal forces whatsoever. Now, what was I writing down there? Steel and G. All right. So my modulus of rigidity for steel is, I'm going to go with 12 times 10 to the 6 PSI. You're probably thinking, what are you doing working in the British gravitational system? I want to work exclusively in the SI system. Well, I'd say move to Japan or Europe or, Australia or Russia, and you could be working in those. But what I want to show is that, there's conversion factors that you really got to memorize. And so the one that I use is 14.7 PSI equals 101,000 pascals. Where does that come from? That comes from 1 atmosphere, doesn't it? That's our standard atmosphere. Atmospheric pressure at the surface of the Earth is 14.7 PSI, and it's also 101,000 pascals. So I use that, and this equals 1 atmosphere. I'm going to extend my little box, and that's what I use. So 14 PSI equals 101,000 pascals. It's a very easy conversion. You know that it's 1 atmosphere too, so it actually teaches you something. But we're going to do this problem using the British gravitational system. So I'm going to, and I'll tell you, especially in mechanical engineering, a lot of this is still going on. A lot of the tables that you'll see will still be in PSI, whether it's for G or tau max. And in fact, I'm going to give you tau max, for structural steel, and that would be 13,500 PSI. And it's good to at least have familiarization with working in the British gravitational system so that you know what's really going on. So we've got a couple, we've got those things. I'm also going to give you another thing. This is twisted. The angle of twist, or the angle of inclination, right? It goes by both names, angle of twist and angle of inclination, is going to be 6 degrees. Of course, we can't use degrees, can we? So I'm giving you a lot of things in here that, if you wanted to work in the British gravitational, in the SI system, you have to change those. But in this one, it doesn't matter which system you're working in. You've still got to change degrees to radians, don't you? Because there's no sine, tangent, or cosine in front of that, is there? It's just the angle. We cannot use degrees when we're working with just the angle, can we? We can't. And we know that from looking at, and I've shown this to you a billion times, right? This is the distance of the arc, that's the radius, that's the angle, but that angle is not in degrees because r times theta equals s, doesn't it? Right? R times theta equals s. So theta has to be in radians. Let's never forget that. I'm going to put that out there. I know that you won't, but I just want to put that out there. Okay, now, so the angle of twist is going to be 6 degrees. What we want to know is, what is the torque? Right? So a couple things we want to know. What is the torque that's being applied to that if I've twisted this 6 degrees, and I know that G is 12 million PSI, and that maximum is 13.5 thousand PSI, the maximum shear stress this can take without breaking, right? I want to find out what is the maximum torque that can be placed on this, right? At 6 degrees. We don't really need the 6 degrees at all. We just need what what the maximum torque is. We know what the maximum thing is. So it doesn't really matter. The 6 degrees, that doesn't matter. But I also want to find out what is the minimum length of this, right, for it not to break. You're probably thinking, oh, he's obviously at Ford Motor or Chevrolet or GM or something, and they're designing a solid torsion rod for the back lift gate on a truck, right? So that the truck comes down and they're putting this torsion rod in, so the truck lift gate is easier to push back up. I'm probably saying, oh, that sounds like a luxury on a truck. Yes, but it wasn't a luxury in a station wagon, was it? And that's what they had on every station wagon in 1980, 1990. They had a torsion rod back there. The problem was that sometimes after a lot of repetition, the torsion rod, or due to corrosion of the torsion rod would break. Then you'd have to lift that whole tailgate by yourself. But I would think that they are putting this in, some type of truck so that it'd be easier to lift the truck tailgate. Anyway, so that's what we want. For this thing to still work, what's the minimum length that I can have it? Obviously, or I should say let's see. Minimum. What's the maximum length? Sorry. What is the maximum length that I can have this? Really, I want to find the shortest, that this will actually roll over at 6 degrees when I, am allowing this to roll out. So what's the maximum length that I could have for this to still be 6 degrees? Let me look at that for a second. Just a second. I'll be right back, but I'm sure I'm right. No, I'm right. That is L max, and if I made L any longer, then that would violate my my maximum angle that I can go. So this, of course, is the maximum angle of inclination that I can go right at failure. That's what I'm basically laying down the line. I don't want this thing to move any more than 6 degrees. Right? That's the maximum it's going to move when I apply the maximum shear stress to steel. I don't want this thing to go larger than 6 degrees. So this is the maximum. If I made this longer, that angle would actually go further, right? I'm going to leave that for just a second. I'll start it up in a second, but because I didn't turn it off for, as far as my timer goes. Let's get back to this now. So what we want to find out is the torque, and we want to find out the maximum length to not violate our 6 degrees. So the first thing that I want to do is I want to look at what that torque is going to be. And so we have our equation, tau equals, tau max, I should say, and we have tau max, equals TR over J. All right. So T then, right, is going to be equal to, or has to be less than or equal to, because we don't want it to break it. So T has to be less than or equal to my maximum shear stress times my polar moment of inertia divided by our outer, right? I think everybody can see what we've got there. We've got tau max, and then oh, what I forgot to give you was the radius of this, right? That's going to, of course, make a big difference. So the radius of the thing is just going to be 1 inch. So the radius of the shaft equals 1 inch. And again, we can, obviously we're working in inches, pounds per square inch and stuff like that. So that makes it relatively easy. So if I were to solve this now, T is less than tau max times J over R0. We know for this example, what a J is, right? J is pi r to the fourth over 2. So let's just write that out. Tau max times pi r to the fourth all over 2 times r outer, right? So we've got r outer, so we can cross that out, and we can cross out one of those. And so we see tau max is equal to, wait, what have I got here? T equals, oh, you know what? I'm sorry. T max, all right, I did solve it there, has got to be less than or equal to 13,500 psi. Oh, you know, I can start that up now. Oops, wait. Yeah, I don't know if I'll get through the second one. We'll have to do a separate thing on that maybe, but let's just see. Tau max is going to be less than or equal to 13,000 psi. And we can, you know, we can put the 2, and this is just going to be pi r outer cubed. So pi times I outer, which is just 1 inch cubed, divided by 2. Now that is a cube. So let's just make sure that everybody sees that the way that this is separated is like this, right? So this cube is on the 1 inch. So that's going to give us inches cubed, isn't it? And that's pounds per square inch. So we're only getting rid of 2 of those. So we're going to have inch up here, and we're going to have pounds. So just don't assume that when you punch all of these together that your units at the end are going to work out to foot pounds, because in this case, it's not, is it? 13,500 pounds per square inch times pi times 1 inch divided by 2 equals 21,205 inch pounds. Yeah, let's not get ahead of ourselves. So really, if we wanted those in so T max, if we has to be less than or equal to, and now we've got 21,000 inch pounds, so we've got 21,205 inch pounds. How do I change that to foot pounds? Well, I know that there are 12 inches in 1 foot, don't I? So the inches are going to go off there. We're going to divide it by 12. And now I have foot pounds. So 1767 foot pounds. Let's take that a little further. What if I wanted to change these 1700 foot pounds into Newton meters, right? Wouldn't we just take 1767 foot pounds and then multiply it by, let's do the feet first, 3.28 feet equals 1 meter, right? Let's do the pound second. 1 pound equals 4.43. Well, I use 3, but it's really 5 newtons, 4.45. All right. So if we multiply those two things through, we end up getting 2397 Newton meters. I'll put Newton meters this time because we did the conversion factor, but really it's a joule, isn't it? 2397 joules. That's right. So I want to sort of circle this. This is, of course, in foot pounds. We want to circle this. This was in inch pounds before we went to foot pounds, and that's what we ended up getting here. And then we've also gone through the conversion to convert that to Newton meters, because maybe the next guy in line works exclusively in the SI system because he doesn't know how to work in the British gravitational system because he never had a professor like me that forced it down your throat. So let's go to the second part of this now. We know what that is. We know that the maximum angle, right? The maximum angle is going to be 6 degrees. Well, what is that 6 degrees? Well, 6 degrees, you know, if we want to turn that into radians, then we want to get rid of the degrees. So let's put 180 degrees on the bottom and let's put pi radians on top, right? So the degrees are now gone. And my conversion, you know, pi radians is 180 degrees. You could use 2 pi radians equals 360 degrees. It would work out just as well. But let's just do that. So 6 times pi divided by 180. Oops, wait, syntax here. 6 times pi divided by 180 gives me 0.1047 radians. And remember, as an engineer, we can't work in degrees. You know, that is not, degrees are not an engineering unit. Those are something that's left over from 5000 BC when it was first created. All right. So that's the radians that we've got right there. And we know that that's a maximum. So that equals theta max. We don't want it to go over whatever this torsion thing is. We don't want it to go over 6 degrees. So what's going to be our maximum L, right? Our maximum L. So what we're really saying is TL over JG has to be less than or equal to theta max, which we know is equal to 0.1047 radians, right? Does everyone see how that all worked out there? So let's figure out what the length length is going to be, the maximum length is going to be. Well, let's solve for length. So we know that the length has to be less than or equal to the maximum angle, right? Times J times G divided by the torque. And of course, that torque we've already solved for, so we know what the maximum torque is. Torque has to be less than or equal to 21/2005. So let's do this. So 0.1047 radians, right, times J. Well, we've got to figure out what J is, but we can say that J is really just pi, right, times R outer to the 4th. I'm just sort of separating it out here and putting things in different places, divided by 2. I'm just sort of writing it all around in the same place right now. I'm going to put torsion over here in just a second. But pi R to the 4th, outer, R to the 4th, because it's a maximum, right, times G now. And G, I'm going to actually put in there as 12 times 10 to the 6 PSI. I could just switch that right now into pascals, and then we could solve this in pascals, or, you know, whatever. Actually, it's that wouldn't work out because we want the anyway. Anyway, I still have to put torque in, and of course, torque we have in inch pounds. So this is in pounds per square inch. We have torque in inch pounds. That should all work itself out. So I've got 21,000. I wouldn't want to put in other words, 1767 foot-pounds because this is in pounds per square inch. So let's make sure that we cancel out all of our units correctly. You know, L, you know, meters to the 4th, or feet to the inches to the 4th here. I'm going to get R0. Well, we know I should have put that in there, right? 1 inch to the 4th. I guess in some ways I could put it in there, but you know, we know that R0, I'm just going to put it over here. R0 equals 1 inch. So as I'm working through here, so L is going to be less than equal or less than or equal to I've actually worked that out, but I'm going to punch it in again for you just to make absolutely sure. 0.1047 radians times pi times my outer radius of 1 inch to the 4th. I could have left that out, couldn't I? Times 12 times 10 to the 6 psi divided by 2 divided by 21,205 inch-pounds. That gives me 93, keep our units correct, inches. It's actually 93.0699. So we could say 93.07, but I'm going to say that it's 93 inches. So we know that this has to be less than or equal to L max. It has to be less than 93 inches, or this thing, if I make it longer than L, it's going to be more than the 6 degrees, which is our design criteria, isn't it? We have to design this torsion rod so that it never rotates more than 6 degrees at its maximum shear stress, right? So we've got two things that we're competing design criteria: 6% angle of twist, and also the material I'm using, 13,500 PSI. So you can see that there's a strong difference there. Now, what I'm going to do for the last minute or so that I've got you is I just sort of want to prep the next thing that we're doing. Sure don't need that line. But what I want to compare is I want to compare 3 different torsion shafts, torsion rods. I'm going to look at a cross-sectional rod. I'm going to look at another rod that has 80% of the inside of the rod cut out, right? Then I'm also going to look at another rod, if I could do this, where I've only left 5% of the outer radius as my thickness, right? So T equals 0.05 R outer. And so that's what we want. We want to look at T there, right? And that being a very small amount of R outer. We want to look at this where R inner equals 0.8 R outer. And then we want to look at this torsion bar where, I've just got R outer, solid. Now here's the thing, in looking at all of those, am I saving cross-sectional area? If I made this, if I kept going in this direction, am I going to save cross-sectional area? Am I going to be able to withstand the same amount of torque with less cross-sectional area, right? So we're comparing these things are all made out of the same material. They're all resisting the same torque. Do I save cross-sectional area by using hollow or thin wall torsion rod? The answer is yes. Yes, yes, in a big way. Are there some places we can't do that? How about the crankshaft in your engine? No, we don't have the room. We don't have the room, and also we've got a lot of flexural loads on that, so we have to use a solid cross-section there. But the drive shaft in your car, only really has purely torsional loads on it, no flexural loads, not that much, there's some. That's why we have to use this instead of using this. We would save even more area if we could use this. The thinner we make the outer wall. Now notice all these outside area radii are not the same, are they? The outside radii of this is much larger than the outside radii of this, is much larger than the outside radii of this. So the radii are getting larger, but the cross-sectional areas are going down. So the cross-sectional area of the thin wall is going to be less than the cross-sectional area of the hollow is going to be less than the cross-sectional area of the solid. And so that that saving material costs and doing the same thing with less, isn't that what all manufacturing really is all about, is to do the same things with less and more productivity? All right, I will see you. Actually, this is a bit early. I think I'm doing, but I'll see you in the next lecture. See you there. It's going to be an interesting lecture comparing those three things. Bye.